Hello, my name is Adam Summerville. I'm at the Expressive Intelligence Studio at UC Santa Cruz, and today I'm going to be discussing early work on a system called Lita, which is about learning to read games by using inductive logic programming for game analysis. So I'm going to take sort of a roundabout way of discussing Lita with sort of all the motivation up front. So the whole goal of this project is automatic game generation with meaning. There's been a few people who have attempted this before. Mike Cook with some of the Angelinas, Mike Trainer, Brian Blackford, Michael Matthias, and Ian Bogost with Game OMatic. And the way that these systems have operated is that a user gives them some set of desired meaning that they wish for the game to produce, or in the case of Angelina, it might come up with it on its own by looking at the news or what have you, or a theme, and then it tries to produce a game. But these sort of operate in one direction. They take in this meaning, and then they do some actions to try to produce a game that produces that. But they don't really understand the games that they are producing, and so the work that this has been doing has been trying to sort of close the loop and create a full feedback loop on this so that the game, we can understand the game and understand meaning from a game, and then so that we can take a meaning and generate a game, and then we can double check and say, does that game match the meaning that we wanted to have? And so that this uses a system called Procedural Streetings, developed by Mike Trainer and others, which is sort of a humanistic process which takes in as input sort of definitions of a game, the entities at play, the resources found in the game, and then combines that with the mechanics of the game. If I press a button, Mario moves upward. And then from that, you make inferences on the game based on that. So the sort of first one are the dynamics. So I press a button, Mario moves up. Well, Mario moves up, he bonks his head on a question mark block that produces a mushroom, etc. So all of these things are working together and interacting in different ways. Then from there we have the aesthetics. So, how does this feel? Does it feel lively, energetic? What is a player going to do? The player wants to jump up to hit the question mark block because it, has a nice sound effect and it feels good, and then it produces a thing that they like. And, it's not just sort of these raw mechanical things moving. There's this theming, so that can flow into the aesthetics. Does it, have a good sound effect? Does it look appealing to do something like that? And then all of these can combine to sort of derive, come up with the meaning of a game. And these can, sort of build on each other. And so meaning can build off of meaning, developing up into higher and higher inference chains. And of course, all of this has this sort of fuzzy blob of culture. What feels good or seems like a pretty thing in one culture might be unappealing in another. So all of these things are informed by the culture under which this reading is taking place. And so earlier work that myself and Chris Martins and others did looked to do this procedural readings process procedurally. And to do this, we developed a domain-specific language for games called Cygnus, which I'll go over in the next section. Then I'll discuss briefly our process of performing these proceduralist readings procedurally. And then finally, I'll discuss Lita and sort of why we are where we're at. So, Cygnus is a language that is embedded within Ant's prologue, so it's a bunch of predicates and terms. So here we have sort of the definitions that you might find in a game, so the predicate of entity, and then inside of that, so you can think of entity as sort of like a class, and then paddle left is sort of a unique signifier that says there is something that in the course of this game specification will be called paddle left. Paddle left itself has no semantics. All of that is defined by how all the other things that in the Cygnus specification. And then you might have resources, and there are other ones too, but entities and resources being the two major things found. And then those come together in the mechanics, which are typically groupings of preconditions and then the results if all of those preconditions are met. So for instance, we might have the precondition that there is a control event, and that control event being the player input of the up arrow being held, and then that's the precondition for the outcome of moving up. And then the result of moving up, perhaps unsurprisingly, is that the left paddle moves north at the speed of 1 unit per second. And so, this is sort of a brief snippet of what you might find in Pong, and there'd be probably on the order for Pong about 38, 39, 40 or so rules making up and definitions making up Pong. And so that's sort of a brief introduction to Cygnus, and now I'm going to discuss how we have in the past performed these procedural streetings procedurally, and then finally discuss where we're trying to go with this. So these procedural streetings procedurally are in the form of inference rules on the sort of ground facts of a game. So say a sort of low-ish level type rule that we might want to make is, what does the player control? So nowhere defined in like Cygnus is there like player controls X, but we can infer it based on preconditions and outcomes. And so, we might say that the player controls X if we see there is some precondition based on a control event, and then that the result of that outcome that precondition is based off moves some other entity. And there are other ways that a player might control the game, or control an entity, but this is one way that we might say that there is player control of an entity. And so this is each of these capital letters is a variable, and then these can be sort of reified in a game in various different ways. So in Pong, it's that the player controls the left paddle, because we notice that when the player holds the up arrow, that causes the paddle to move north. Or say in Kaboom, the player controls the bucket, because when the player holds the left arrow, then the bucket moves west. And then finally, say there's some sort of single button asteroids or something, the player controls the spaceship because the player clicks a mouse button, and then that causes the spaceship to move forward. And so each of these would be different ways that you might find this in the sort of ground facts of a game. And so we can perform these inferences, and so this is a very simple one. It's sort of predicated only on the ground facts found in the game. But these can be chained together in varying levels of complexity. So this is like just sort of a mid-level complexity inference chain about doing some sort of basic player modeling, which is that the player will do something by holding the cursor near something else, because the only way that they move things is that they can control the mouse, and then the only way that they do a good thing in the game is that by pushing new ideas towards producers. And so anyway, you get this big long chain, and so 7 rules here for a pretty relatively simple reading of what the player will do. But these can be chained together in larger and larger inferences chains, and so this is some stuff that we have done in the past. So now I'm going to finally discuss Lita, and where we're at, and where we hope to go. So Lita takes in these sort of Cygnus-specified games, and then some inferences that a person might make about those games. So, say we have Pong, and then say we notice that, the player controls the left paddle, the computer controls the right paddle, and we notice that the points for the left-hand side are good, because those are what are good for the player. So Lita takes those in as input, and then the goal is to produce these rules. So trying to learn that the reason why the player controls the left paddle is because we notice in the game that it is the only thing for which there's some control event that fires, and then that results in that thing moving, or that the computer controls something if it moves and the player doesn't control it, or that something is good if there's a positive resource check on it for the game being won if if those points pass a high enough threshold. And so these are the types of rules that Lita produces by looking at these sort of game definitions and higher order inferences. And so the way that Lita operates is it first takes in all of those ground facts of the game and observed properties, and then produces a graph structure over that. And so then it starts at those higher order inferences and then traverses this graph. So we might start off here at, the player controls the left paddle. And then we traverse this graph in sort of increasing order of complexity, given that there's sort of this notion that the sort of minimally complex rule that fully covers our set is going to be the best rule. So if we get full coverage of the facts that we have and it is the least complex, we hope that that will be the best rule in general. So, here we have, player controls paddle left, and then, so say we traverse to the entity paddle left, this definition. So we would make a rule. We notice that there's this paddle left on both sides, and we turn those into variables via an abstractification process. So we get, player controls X if entity X. And so then we test that rule to see what our coverage is. And we see in this case, it's not that great. We do get that the player controls X and gets paddle left, but it also gets the right paddle and the ball. And so this rule gets thrown out, and we continue on in the traversal. And now we perform a breadth-first traversal of this graph. And so then we come across, the player controls something if it moves up. So then we get, player controls something if there's some result that results in that thing moving. Well, again, that's incorrect because the right paddle also moves in this way. And so we wind up sort of coming across these rules and throwing them out as they aren't good. But eventually, we do come across, that the player controls X if there's this precondition that, the player does some input, and then that results in that thing moving. And so then we perform a sort of subsumption process where we test ways of removing the functors found in this definition, which are the things of which don't have the sort of only base terminals inside of them. So in this case, the moves, the player input, and the control event that then contains within it the player input. And so we test each of these, trying to turn those themselves into variables. Again, the goal being to find the sort of minimal rule that covers the set that we're looking at. So in this case, we see how those would sort of be subsumed. The moves gets thrown out because we've now orphaned the player controls X. So that's not considered because it can't possibly be correct because we can no longer find an X based on what we have on the right-hand side. The next one, we see that indeed in that case, it actually is the best. It does work out well. It still is correct. The player input is just one way of getting player input. There are other ways that there could be control events like clicking or what have you. In this case. And then finally, we see that if we try to subsume all of that, that just is looking to say if there's some precondition that results in something moving. Again, that's incorrect because there are other ways this could move, as we just saw in the last one, with the right paddle moving. And so this is sort of where Lita is at currently. We can traverse this graph that sort of automatically infers the types of things of the variables found, and then search over that structure, and then find sort of the minimal rule set that covers the positive examples that we give. So it's still very early work. It does this exhaustive breadth-first search, and so for the future, we'd like to make Lita more expressive. By utilizing more ASP-specific language constructs, by counting things, by checking if two variables are equal or not equal, or what have you. And then finally, we'd like to make Lita faster, better search pruning, better heuristics, so that this exhaustive search is not so difficult. Thank you.